Alright, so welcome back. This video we're going to change pace a little bit, and we spent a lot of time focusing on design examples and using LRFD methodologies. But one of the other more important issues that still needs to be discussed, and that kind of falls outside the realm of AISC, is the design criteria for structural adequacy. Now, we define a structure being adequate if it can do two things. Is it able to carry the supported loads? This is what we call the strength criteria, and this is where the LRFD calculations that we've been looking at will fall under. And then the second category is serviceability. Okay, and can it perform its intended purpose while holding those loads without experiencing some other issue, whether it be excessive deflection or vibration or some other non-strength issue. Examples of this in concrete, maybe I'm trying to control crack widths so cracks don't get too large or too open, too wide, and allow some sort of corrosive agent to get in and affect the rebar. Now, like I say, cracking isn't generally a concern in steel, but those are some of the types of issues that fall into this category of serviceability. Okay, now in the case of the loads for all of these, you'll remember that the LRFD methodology says that for the strength calculations, I have to factor the loads. These are those load cases of 1.2 dead load, that PU is 1.2 P dead plus 1.6 P live, something like that. We use those to do our factored loads. Okay, and then with that, we compare it to the capacity side, the reduced phi, phi PN, and the corresponding equations that come out of the AISC specification. Okay, for serviceability, it's different. Okay, we don't factor the loads. What we do is we use the service loads, or an unfactored load case. So we've got to be very, very mindful of that. Right now, okay, the first thing I'm going to show you is kind of some of the features of the AISC manual that they do to help you with the structural analysis, because the structural analysis can be somewhat kind of time consuming. I'll slide this down here a little bit so we can see it. Okay. And we'll show you probably one of my favorite items in the AISC manual that has to do with structural analysis. Okay, and in my opinion, these couple of pages that contain these will be worth the money, worth the price of the manual itself, because it does such a good job of kind of compiling all of these values together. So what we're going to do is we're going to move into kind of show you some of these, and I'll show you a couple of the simpler ones on this. We're going into table 3-23. Okay, and so if I go through and if I try to zoom this in a little bit, let's see if we can get you a little bit more. Okay, there's a set of page upon page of these simple cases, and if you remember from your structures or your statics classes, coming up with the equations to draw shear moment diagrams, or to calculate deflections, or find support reactions, or determine the location of the maximum displacement. Okay, well, AISC has page upon page upon page, many pages of these. In fact, there's like 46 different cases that they start to tally of common structural setups, so that you don't have to go back and do these trivial calculations as part of your analysis. It kind of speeds the process up. And so I'll show you the simplest one. Okay, and this is case one, is the simply supported beam. It's uniformly distributed load, and you can see that here's the diagram, and they show the support reactions, and then they have the shear diagram and the moment diagram. And then what they do is they tally up a bunch of parameters based off of this idea of a uniform load over some length of L. Okay, and so we have things like, oh, well, the reaction value then is WL over 2. Okay, and boom, you've got it. Okay, the shear as a function of X is this equation. The moment as a function of X is this equation. And then, of course, they even give you the maximum moment and tell you where it's located at, okay? And so every one of these cases will have information like that associated with it. So it really speeds up the process if we look at what we're trying to accomplish. Get our light set here maybe a little better. Okay, all right. Okay, now, perhaps the most useful in all of these will be this guy down on the bottom. Okay, and again, I apologize, it's a little blurry, but if you've got the manual, you can play along at home. Okay, and this is delta x guy, and what that's the equation, this big long equation, wx over 24ei times l cubed minus 2lx squared plus x cubed. Okay, this is the equation of the elastic curve, or the deflected shape that this member goes through under that particular load. And the thing that's cool about it is it's at every position of x. All right, so all I have to do is, note on the diagram where they're measuring from. So x in this case is being measured from the left support, and that's pretty standard for all of these, but you got to look at the picture to make sure. Okay, and then all I do is I take this equation, I watch my units, and then I convert, I plug in my value of x. So at the support, that's x equals 0. Over here, it's x equals L. If I want the midspan, it's L over 2. And I can choose any point, and I can instantly get the equation of that elastic curve. And that's very, very handy. And it saves you having to do all those classic structural analysis methodologies that we look at. Okay, now, if we kind of go back through and look at some of the other tables that are present in this. Okay, get myself zoomed back out here a little bit. A little much. Okay, the table's broken down into, like I said, there's about 46 different cases. And the ones that are most handy are obviously these simple cases. And they cover, from cases 1 to 23, cover the simple spans. Is it a uniform load? Is it a point load? So forth and so on. Okay. They also get into some cantilever cases, which are 24 through 28. Okay. And if I show you one of those, these are the kind of the cases that we're looking at here. So this is the uniformly loaded on the main span and the cantilever, support here, and then the free end is at this end. Okay. And then for all of these, it gives you the equations for the reactions, the equation for the shear in the main span, the equations for the shear on the cantilever, the moment in the main span, the moment on the cantilever, and all that's tabulated for you. And again, these delta x functions. So I have the elastic curve in the main span, and I have the elastic curve here that is on the cantilever. Okay, and so all of those are really, really handy for us. Okay, and then the next piece that we have, if I flip a little bit further, that's pretty useful, is what do you do about continuous beams? And so one of the things that we look at is, pull this back down in a little bit, is starting on case 37, these are the continuous beam cases, okay? And you'll remember that, depending on how a beam is loaded, we get into things like pattern loading, what do the equations look like? And so they tally these up for you very, very simply. So this is a uniformly loaded 3 equal span beam, okay, with a uniform load of W on it, and then it says, oh, well, this reaction is 0.383 W times L, and this reaction is 1.2 times W times L, and they tally up all of these indeterminate support reactions. This is 1 degree indeterminate. Okay, so we can't even solve it with basic statics. We have to do our mechanics approaches, but they've done all of that for you and tabulated all of these for you. And then going one step further, once you have these reactions tallied, I can go in and I can draw the shear diagram for this particular load case, a 3-span load case. And then if I have the shear diagram, I can come in and I can do the same thing for the moment. And they give you the values. So at this support at 0, here's the value of the moment at 0.0735 WL squared. Here's the negative moment, minus 0.117 WL squared. And it's the moment diagram that comes from this loading. And they repeat the process for the major combinations of 3-span continuous beams. Okay, so if we look at some of the lower ones, you can see, okay, well, this is the checkerboard pattern where I have a loaded span here, but nothing here, and then a loaded span here, and then same game. Here's the shear diagram with the respective values, and here's the moment diagram with its respective values. And then you get to the last case, which is all 3 spans loaded. So between these 3 cases, I can capture the maximum moments at the midspan, the maximum moments over the support, and then I can even, and with that, I can then go in and do my design. So these tables are very, very, very useful. Okay, and then the last table, it goes one step further. It even goes in, and in a similar fashion, it does the 4 spans, and then the patterns associated with it. So here's 2 on, 1 off. Here's the checkerboard on, off. And then, of course, down at the bottom would be your 4-span fully loaded. Okay, and so there's all sorts of useful information in these, and being able to generate the shear moment diagrams is critical to being able to do a beam design problem. Okay, so these tables are fantastic for that. Okay, now, just to kind of point out some of the cases that are probably more commonly used than others that I find myself going to are the three cases located at case 1, case 8, and case 21. Case 1 is the one I showed you. It's the uniformly loaded distributed beam. Now, be careful. They write out the nomenclature as W times L. This is actually the total load acting on the beam. Okay, but in the equations, you'll notice that we want to make sure that W has some sort of units like 1 kip per foot, or 1 Newton per meter, or whatever the case may be, and then L would be the span. That would get you the total load. Okay, the other one that's pretty useful is a point load applied at any position. Okay, now again, they're measuring everything off of the left, and so this particular case 8 will have a point load at a distance of A from the reference, okay, and B from the other reference. And then with this, you can go in and it will calculate, what's the equation of the curve in this span, what's the equation of the curve in this span, and so forth and so on. All come out of those tables. They have it all tallied up for you. It's really, really nice. And then 21 is also very useful, and this is a cantilever, okay, with a point load somewhere on the cantilever, in this case A from the free end, and they're measuring X from that free end, okay, and then B from the support. Now, you've got to be careful with this guy because we don't always have a cantilever on the left, right? So maybe this beam is flipped over, and so you've got to kind of keep your eye on what this X reference is. Okay, so with all of these cases, we can, for the very simple stuff, it's really, really easy to figure out what the deflections are and save yourself some of the structural analysis, or even having to go in and build a model in the computer software of your choice. Okay, now what do you do for more complex loadings? Okay, and that brings us back, if you remember back in mechanics, we talked about something called method of superposition. Okay, so to do this, we're going to make some assumptions on all of these. It's the old LEIH assumption that it's a linear system, it's an elastic system, it's isotropic and homogeneous. Okay, that we have a constant prismatic cross-section, and all of those become factors in this. And so the idea here for superposition was, well, what if I have a beam that is a uniform load with a point load on it somewhere, that I can break this into simpler cases that make up these results. Okay, and so here I have a simply supported beam with a uniform load on this, plus then a simply supported beam with I lost my pencil lead. Okay, with a point load P acting on that. Okay, and so this becomes a very simple case. This is our case 8, and this guy becomes our case 1, and then those two guys added together give me the combined effect that we're after for our true loading of the beam. Now, one thing we got to be careful with the method of superposition and these AISC tables. This methodology, all I have to do is come in and find the reactions associated, with this guy, and so this plus this would be this value. Okay, so this methodology works for finding reactions. It works for finding the generalized moment equation, or the moment as a function of X, and it also works for finding the displacements as a function of X. Okay, where you have issues is with the maximum values that are also tabulated, or where the peak value is, a delta max and a maximum moment. Because what can happen is, if this point load is in the middle, then the maximum deflection for this case is at the same location as the maximum deflection for the uniformly distributed case. But if this guy creeps over and is more towards one side than the other, then the maximum is no longer in the middle. And so I can't take a maximum value on this one and add it to a maximum value on this and get the maximum for him. It doesn't work. Okay, so there are some issues with that. Now, like I say, for this example, if that load is exactly in the middle, I can, but in general, you've got to be a little bit more cautious about what we're doing. So basically, we're going to say if the maximum occurs at the same location for all of the subparts, this one had 2 subparts, or maybe I have some additional that are also in this, then I can add up, and get the maximum values if they're all at the exact same point. Okay, superposition will still work. So that's a pretty useful criteria. Okay, again, a little bit of review for mechanics, a couple of things that useful relationships that will happen that you can recall is that for just any beam, the deflected shape, we call that the elastic curve. Okay, and then at any point X from our reference, and in this case my reference is at the left, at any point X, that's my displacement. So this Y as a function of X defines all of the deflected shapes. Now this is an arbitrary loading with a point load and a distributed load, whatever the case may be. Okay, if I can generate that Y of X, okay, and incidentally that Y of X equation on this, Y of X is delta X in the AISC manual. Okay, so all we can do is that, say I want the slope. Well, we can recall that the slope of the elastic curve is the same as the first derivative of the equation of the elastic curve. This is your basic calculus, right? Slope is the first derivative of a function. So, this is f prime x and y of x is f of x. That's the relationship that exists. So if I can generate the delta x equation, then all I do is take the first derivative of it. I can come up with what the slope is at a given point. Okay, and then likewise, if the shear is a function of x, if I can generate the moment equation, the first derivative of that will get me the shear. And so we can take advantage of those relationships just using some simple AISC tables. And AISC doesn't tally slope or shear directly as functions of x, but you can compute them once you have the full equations work together. So let me show you how we'll do a real quick one here. I'll show you how to do it. Okay, and then we'll come back in and we'll look at some other issues. All right. Okay, so here's our superposition example. What I have is I have a cantilever on one side. I put a uniform load with an intensity of W, okay, acting on the main span. That's the span between these two supports. And then I'm going to put a point load out here at the end of the cantilever. Okay, now the manual says we're going to define two different stationing points. Okay, so X is measured from the left support for the main span, and then X1 is measured on the cantilever, and it comes from this interior support. Okay, so all we're going to do is we're going to come up with the systems that allow us to work on this. All right, so I have two systems. Okay, so I'm going to break it up into a uniform load on the main span. Okay, that will get me, this is my case 27. Okay, and then I have a point load out on the end of the cantilever, and that's my case 26. So they're all on the same page. So if you go and you look at each of these, okay, for the main span, for my region 1 on this, I can calculate the equation of the elastic curve by taking the equation associated with this diagram, which is this equation, Wx over 24EI times L cubed minus 2LX squared plus X cubed, okay, plus the effects of this guy, okay, which is PAX over 6EI over L times L squared minus X squared. Okay, so if I add these two together, this plus, that's the superposition part. Okay, and so I can come up with my equation for my elastic curve. Okay, similarly for the moment, I know that the moment as a function of x within this main span, okay, is Wx over 2 times L minus x. Okay, and will get me the moment that comes, the maximum moment that comes out as a function of x from this distributed load. Okay, and then I also get my load PAX over L for the deflection on this case as well. Okay, and so that will get us kind of our peak moment that's happening on this particular beam. All right, okay, and then once you have that, you can come in and we can calculate the slope doing our first derivative, and that's that big long monster bit of algebra and calculus. Okay, and then my Vx, I can do the same thing. All right, okay, and then likewise on here for region 2, this would be the cantilever region. I can play the exact same game on that. And again, these are all equations that are coming out of those respective cases of 26 and 27 in that table 3-23 and the AISC manual. Okay, so super easy. And so a little bit of the structural analysis is complete. Now, what do we do with it? Okay, and this is where we got to be a little bit mindful on what we do. Okay, now deflections, this is our serviceability criteria, okay? And as we said earlier, it controls things like cracking and vibrations and deflections, okay? And generally, these are prescribed by local building codes, okay? Local jurisdictions will have minimums for certain scenarios, okay? The thing to remember is that in all of these deflection criteria, we're going to be using the unfactored loads, okay? These are what we call service loads, all right? Because it doesn't make sense to put a 1.2 factor on a dead load if all I'm doing is measuring displacement, because the 1.2 has no meaning. Okay, we want to know what the true deflection is under the true load. And so some of the more common ones that many jurisdictions use, okay, are the live load deflection and then the total load deflection. And so what we're going to do is we're going to look at the live load deflection of a beam or of a member that's in the roof is limited to L over 240, where L is the span. So if this was my basic beam, L is that guy, okay, and so that's my span length, if you will. Now we got to watch this. This L is supposed to be measured in inches, so if this is 20 feet, then I need to multiply by 12 to come up with a limit for the roof deflection, and I'll show you that in an example here in a second. Okay, another, for something with a deflection critical a deflection critical displacement, for something, say, like a plaster ceiling or some material that can't withstand excessive deformation, sometimes you can crank this up and they'll actually go up to like L over 360. Most floors are L over 360, though it's not uncommon to see this value go up as well. If you have fine Italian marble that's costing you $1,000 a square foot, you might want a little extra insurance, and maybe I crank this up to L over 480 or L over 600 or something. It's your best engineering judgment what you need to set this limit to. But as a minimum for serviceability, these are the prescriptions that are required. So for live load, it's L over 240 for the roof and L over 360 for the floor. Okay. Then they go in and they look at, they can also do the total load limits. And this one's not as important as the live loads, because in steel, what I can do is I can actually pre-bend a beam so that the dead load deflection is taken out. I bend a beam upward, so when I build it, I camber it like this, such that this is the delta D amount. So I basically take that out so that when I put the dead load on it, it deflects back down in such a way that it's now flat across, at the time of the dead loading. And the dead loading is a permanent load, so it's basically factored out. So that's why this one isn't as big of an issue, okay? But you still do kind of need to check it if you don't pre-camber this thing. Okay, and so those limits are then L over 180 and L over 240 respectively. Okay, all right. Now, for a couple of cases that we want to kind of look at going back in, the delta max on this guy and on this guy are given by the following equation. So these are just two that are just worth memorizing. Delta max for a uniformly distributed, simply supported span is 5 over 384 times WL to the fourth over EI. Okay, and then for a point load at the mid-span, it's the value of the point load P times L cubed over 48 EI. Now you got to be really careful on this, because in this, L is usually in feet, E is in KSI, and I is often in inches to the fourth. Okay, so we've got kind of a units discrepancy, and this L cubed and this L fourth can kind of start to play, kind of have some issue. Okay, and to further complicate things, the calculations we were doing in our code, okay, on this, the delta was in inches. Okay, so generally what I do is I convert everything to kips and I convert everything to inches, and then I do my calculation. Right, that W gets a little tricky because even W himself is often measured as KLF, or kips per foot. So there's a foot hiding here and a foot here, and it gets a little tricky. And we'll show you an example of how we can start to kind of work our way through it. Okay, all right. So how do we make use of this? Okay. We come in. Basically, all you do is we calculate our delta max, which is our limit that comes from the code, okay, and I compare it to the delta that I get from the AISC tables. But what we do is, when we're in the design process, we don't know the section size. And if I don't know the section size, then I clearly don't know the I value of the beam that we're choosing. So I becomes kind of a design parameter that we can choose. All right, so let's take a look at a real quick example here. We'll run through this fairly quickly. I'm going to do a serviceability check on this beam. It's 20 feet long. I'm going to put a live load of 1 KLF. Okay, we're going to say that it's our beam in the roof of the structure, which means then that my delta max is limited to L over 240. Okay, my delta live load that comes from the AISC table, and in this case, this is my case 1. Okay, and this is my delta. What would be my peak deflection coming out of the AISC table is 5 over 384, and it's WL to the fourth over EI. Okay, again, we don't factor the loads on this. Okay, and I'm going to be looking at my WLL on that guy. Okay, now if I compare my code limit to my AISC limit, I can write an equation that looks like this. We're going to take L over 240. Remember, L has to be in inches. So I'm going to take 20 feet times 12 inches per foot divided by 240. It turns out that guy is just 1 inch. So a 20-foot long beam in a roof is limited to 1 inch of deflection. Okay, that preserves our small displacement theory, and things remain small, and we won't violate our LEIH, okay, that we talked about earlier. So we're going to say then that 1 inch, this is the maximum, that it has to be greater than or equal to the actual displacement that comes from the beam that we choose and the loads that are on it. So I compare that to 5 over 384. Here's my W, 1 KLF. Now, this quantity right here is my L to the 4th. But you'll notice what I did is I factored out one of them, 20 feet, so that it would knock out the foot on these units. Okay, and then I have 3 left, 20 foot cubed, and that I convert to inches. So that's why there's a 3 here and not a 4. Okay, because this 20 goes to knock that one out. Okay, and then I divide that by 29,000 KSI, which is our E for steel. Okay, and then I have an I minimum that's required for this particular beam. And again, we don't know what this value is. We haven't designed it yet. All right, so to make sure that we have our displacement limit in check, we have our 1 inch greater than or equal to, in this case, if I do the math, I have 124.1 inches to the 5th over my I minimum value. Means that to make this true, I min, okay, has to be 124.1 inches to the 4th. It can be larger, okay, but if we go any smaller, I'll violate that code requirement for our basic displacement, okay? And so in this way, the way that we've solved for this I minimum, I min now becomes an additional design parameter, and this will cover our serviceability requirements. Now, again, we haven't designed this beam in any way for the maximum moment or the maximum shear or any of the bearing issues or anything. We haven't done any strength calculations at all. This is just what's required for serviceability. So we could go through and do our strength design, and then basically we find the first one that has all the strength parameters, whether it's whether I'm looking for ZX or whatever the case may be from our previous lectures, okay, and I'm going to use that and this in conjunction to help choose my size, okay. But for our case, all we're going to look at is pulling out the I minimum, the I min of 124.1, and so I went through and I ran the table real quick and I started kind of at the smallest sizes that I could find. So a W8 by 35, I can meet that requirement with an I min of 127. I mean, we're right at the line on this one. Okay, but if I go to a W10 by 26, I get an I minimum of 144 inches to the 4th. Okay, and if I keep increasing the size, it goes to W12 by 19, I minimum is 130, and then I get to my W14 by 22, my I min is 199. Now, you'll notice that when we started at the W8s, it got more economical the deeper I got, and that's because I gets a huge boost from the depth of the beam, all right? When we do our parallel axis theorem, that D, that AD squared term in parallel axis theorem, that D is what drives the I value more so than anything else. So you can see we went from a 35 pound per foot to a 26 pound per foot to a 19 pound per foot option. And then it went back up here, and this is generally the trend. As I get deeper, these numbers go down. Now, we started out fairly small to begin with, but if I had a real high, W8 by 100 and something, then these would come down and this 14 would become a more economical choice. It turns out that this 14 by 22 is the minimum in the sizes of the W14s in the manual. All right, so for us, for this particular example, I would choose the lightest member, and I would choose this 12 by 19 as my optimal. Okay, and so that's how we start to do that. Okay, but again, you still have to check for strength. So the process isn't hard. It's just understanding that you have two sides to the equation that we talked about back here. Okay, I've got to have my code, my limit of what's allowed. And again, this comes from the code or this comes from your engineering judgment. Okay, like I say, I've had design problems where I was using L over 600 because we had a deflection critical situation. Very sensitive laboratory equipment might have an even bigger limit on this because we don't want excessive vibrations. But whatever these limits are, that's how we do it. And then I compare it to my deltas that came out of those AISC tables that I just showed you. So anyway, that's kind of our basic rundown of deflections. It's just another piece of the puzzle. It's another parameter that has to be considered. And at the end of the day, you have to have enough adequacy for both strength and these deflection or serviceability conditions to have an adequate member for your design. So anyway, as always, let me know if you have any comments. Leave that down in the comment boxes below. And otherwise, we will see you next time. Thanks for tuning in.